Yes, so I'm going to talk about the transition to the ultimate regime. As you know, already in 2012, we already talked about this, so this is kind of a follow-up on the talk we presented in Hong Kong. Before I go into this, I mean, we got some funding from the Max Planck Society to build the whole facility. We're very grateful to the Sonderforschungsbereich, so the Collaborative Research Center 963 for the support, which is supporting us with one personnel position, which made also possible the rotating, well, let's put it this way. The Sonderforschungsbereich triggered a instability that made us to make rotating convection. Let's put it this way. And so I put Günther down as being part of the Max Planck Institute, which he also is, and Günther's shaking his head. I don't know why he's shaking his head. I better go on. Pardon me? None. Well, Günther, of course, is in Santa Barbara, so as you all know, but he spends a big part of his time working with us here in Göttingen. And but before I do that, I would like to take this occasion to dedicate my talk to John Lumley, who passed away 2 days ago at Cornell University. As you all know, John was a pioneer in fluid dynamics. He was the one who wrote one of the most important. Tenikis and Lumley is still one of the books that if somebody wants to do fully developed turbulence and pipe flows, this is what we read. And he was one of the winners of the Fluid Dynamics Prize, and I just thought I should mention it briefly here and say that John was very important for me at Cornell. He was always the solid person in the background. He said, Eberhard, just do it. This was his, he said always, I wouldn't do it, but you should do it. That's what he always said. And he always was standing behind me and gave me some support in my crazy things that I was building at Cornell. And so I thank John a lot. And so I thought I should mention this. So let's come to the topic of the talk. What we want to do is, what we want to study is, as Zhao Zhou already said, we will look at turbulent Rayleigh-Bénard convection, and as most of you know, it has been predicted for quite some time by Kreishnen and others, and later also by Grossman and Lose, who made predictions for Prandtl approximately 1. What we know is that there should be a classical regime where the boundary layer is laminar, and then possibly there should be what was called by Castor and others the ultimate regime, where the turbulence, the boundary layers are actually viscously unstable, they're turbulent, and the phenomenon of the flow should dramatically change. The scaling properties should change and so on. The issues we have with this is that the way to get these high Reynolds numbers, it would be nice to actually measure in some geo or astrophysical flows or have some real huge Rayleigh-Bénard experiment where we could get the Rayleigh number really up and finally get some real scaling and see what's really happening. And of course, it would also be nice to look into the flow. And so what you do is what is predicted is that in this range for a Prandtl number 1 fluid, the Nusselt number in the classical regime should scale something like Rayleigh to the 0.31, and the Reynolds number should scale like Rayleigh to the 0.42, while the Nusselt number due to log corrections should scale in the ultimate regime like 0.38, so the difference is not that huge, but the Reynolds number should scale like 0.52. So like a half. And hopefully there's some other signatures in the flow that we can see when we go through this transition, and we can measure some other things. So the question is, what experiments can one do? And one experiment that we do here in Göttingen is, what we decided is that we like room temperatures, so we like temperatures where, remember, when you calculate the properties of gases, what counts is not the relative temperature, but the absolute temperature, so it's something like 300 Kelvin. And so having a fluid that is calculated at 300 Kelvin, and you know the temperature very precisely and very good, at least that gives you some nice properties at room temperature. You don't have to hassle with low temperatures. You don't have to hassle with helium. This is the other alternative that you could do. And when you put the numbers in for gases, for compressed sulfur hexafluoride, so you have a molar mass of about 146 grams per mole, and we build an experiment up to 3.4 meters, so we make it very high, and you go with the pressure close to about 19 degrees. You have to be a little bit careful that you don't get condensation, because you're very close, you're somehow close to the liquidus line, but nevertheless the system is very Boussinesque, as I will show, And for this, you get a Prandtl number 0.8. And then if you put all the numbers in, what you realize is that the Rayleigh number goes like quadratic in the molar mass, which is over here, and of course cubic in the height of the cell, and quadratic in the pressure. And all this tells you that if I use a gas which is very heavy, has a very high molar mass, I'm at room temperature, I get a very high Rayleigh number. So what we did is we built the following experiments. I put this in here. This is a YouTube movie that we made. This is a New Journal of Physics. Zhao Zhou is walking through the facility, is even standing in the facility and tells you what's going on. So if you want to see it in the video and not in real time, you can go here. But what we do is we do 3 types of experiments. The first one was that we did was gamma under half, where we had roughly this Rayleigh number range up to 10 to the 15. And then we had gamma equals 1. The nice thing about this device was, which we discovered later, is since it's the U-boat, it looks like a U-boat. To give you the reason why it's called the U-boat is because the design engineer, Artur Kubitschek, I think, called it a yellow submarine when he selected the color. And then I was objecting and said yellow is awful. But what got stuck was the submarine. And since then, this thing is called the submarine. Also, it was Günther who caused me to build this little tower here. Without Günther, the turret would not be there because I just wanted to build a room of this height. But then Günther said, why don't we put a turret on it? And now the turret has gone really long because we also do aspect ratio 1/3. And so what you have here is what we did is we took this experiment here. We got an extension tubing, which we put inside. And then on top of this extension tubing, we put the lid. And then this way, we could extend this whole experiment to 3 meter 30. And as you notice, is you take this cell plus this cell plus all the thermal shields. Then you take the bottom plate of this one, but you take the sidewall of that one, you put that sidewall on top of here, and suddenly you have an aspect ratio 1/3 experiment. So this is how it worked. So in reality, then, it was empty over here, as you can see. So these are the 3 experiments that I will talk about. And just to explain to you that this is very painful, building these experiments actually is tough, as all of you know who are doing experiments. The people that do numerics would know. But what you have to do is you have to put an awful lot of thermal shields on the side to make really sure that the heat flux goes to the bottom plate. So if you want to measure Nusselt number, which is of course the heat flux, if you want to do this, you have to make sure that the heat is not going out to the side, so that everything is going through the fluid. The sidewall is made of plexiglass, and so here you see the copper plates. There's also a little gap here. This is where we have a plastic plate inside where we can measure the temperature drop from this plate to that plate. And by doing so, we can measure the Nusselt number. And then we can also compare this, what you naively would calculate just by the temperature, by the heat flux that you're measuring, by the heat you put in. And it turns out the 2 numbers agree well. The top is, so the bottom is electrically heated. The top is cooled by cooling water. You see a slight asymmetry in the design. Up here, we don't have quite as many thermal shields. There's also a water gasket running through here. There's another, depending on the design which we use, there's a plastic plate inside which is glued down to this plate here, and then we run cooling water through it and do it so. Here you see Zhao Zhou while assembling the experiment. If you want to see this, Dennis van Gils right now is running, and Zhao Zhou, and we are running an experiment next door. You can see this whole thing rotate at about, 4 rounds per second. And one round per 4 seconds. At least this is what, Dennis, this is what you had said to. It looks pretty scary, to be honest. It's not so bad. Okay, and so what we have done is, so we have done these different experiments. The design of all these experiments is the same. The only difference is that the aspect ratio 1 cell has aluminum plates. So the very old experiments that we did had aluminum plates. Then later we said, well, perhaps we shouldn't trust these aluminum plates because they have no good not as good a thermal conductivity as we could do with copper. Then the economy dipped and we bought a lot of copper. It was cheaper than the aluminum at the time, which was amazing. And so we have a beautifully machined copper plate. And then we realized the results are just the same. So it makes no difference whether you use copper or aluminum. Both of them seem to be good enough conductors, or at least within the range of conductivity, you get the same results. That's all we can say. And so the question was, there has been some discussion about Boussinesq conditions in these experiments, and I would like to talk a little bit about this. So Ladek had been found in low temperature, in his low temperature experiments, that non-Boussinesq effects are quite important. So I would like to, what we did is we had 8 thermistors in the middle of the cell. They were all at the sidewall. We looked just at, for this is aspect ratio half. We just can measure or average the temperature along it. So we have 8 thermistors sitting there. And then to see what the bulk behavior is, we put in another 4 pairs of thermistors symmetrically with 180 degrees mirrored. So this is this opposing one, and so on and so on. These thermistors are spaced at 1, 2, 4, and 15 centimeters away from the sidewalls, while the blue ones are all spaced very close to the sidewall on the side. And so what you then ask yourself is, how much does the mean temperature, the normalized, so you take the mean temperature averaged over all these thermistors, and you ask how much does it deviate from the mean, and what you find is that, because this is what you assume in the approximation of Boussinesqueness, what you find out is that the mean temperature is slightly off by 0.028 degrees when you normalize by the temperature difference. But as I pointed out before, since we calculate all our properties of our gases by the absolute temperature and not by the temperature difference, one could also normalize by the absolute temperature. So you take the mean temperature plus the absolute temperature, and of course if you divide by a bigger number, then you get smaller numbers here on the side. Now we believe that this is the right way of doing it, because the pressure, every parameter that we calculate is calculated with absolute temperature, not with relative temperature. Because, 7 degrees means nothing if you calculate a mean temperature. It could be 20, who cares? It's still a mean temperature. And so normalizing by the temperature difference is, in my opinion, not so right, but I think this is much more reasonable to do. And just to show you how this variation, so here again, this is the temperature averaged in the center minus the mean temperature divided by the absolute temperature. If one plots this out, what you find is that as a function of delta T, and of course the non-Boussinesqueness, the variation of the fluid parameters should go up, and as you find, it keeps going up with increasing temperature difference. So this is, in all honesty, the data that you find for the variations of the mean temperature is a function of delta T. If you have questions to this, we can talk about this in the break. So what I now want to report first is the measurement in the taller experiments, which is 1 meter 10 and 2 meter 20 high. What we did is there's 2 thermistors in this experiment. I should mention that these thermistors, part of this data was done with larger thermistors where there was some averaging going on. So we know that there's been some averaging. But we think that some of the results, actually most of the results are still very, very valid for the Reynolds number because it doesn't have an impact. And so what we have is about a quarter height. There were 2 thermistors. They had a separation of 30 millimeters, and they were 1 centimeter away from the sidewall. And in this experiment, we can go up to Rayleigh roughly 10 to the 15. We can go down to 10 to the 12. We could start to evacuate things. We could put in very light gases. We could possibly, with a vacuum, go lower. But typically, we have been in this range. And so what we found was this. And so this is the Nussel number corrected by what I told you before, the 0.312. And what we find is actually, we have some more data over here with different gases, but what we find is that this is very well fulfilled. And then there's a transition region. At about 10 to the 13, something seems to be happening. And then finally, when you go up in the Nussel number, then you reach a region which might be consistent with the power law of 0.38. So there's clearly first nothing, it's flat, then there's a transition region at the Nussel number, and then finally you might find something that's close to 0.38. Now, one may say that this is not very conclusive, but what you can do is you can measure with these thermistors the effective Nussel number, and where U is the mean flow and V is the fluctuations. And once you do that, what you find is that the Reynolds number, normalized by Rayleigh to the 0.5, if I would not have measured up to here, I would say, well, who knows? Because you see that the data fluctuates like mad. It just goes back and forth. We attribute this to a strongly fluctuating mean flow over short times because this experiment, the mean flow was never aligned. It was swashing around. There was a lot of activity in the experiment. But then suddenly, out of some reason, all the data points collapse. And this is a very strong signature that something must have happened in your experiment if you go from something that fluctuates a lot, where you have different... So look at these points. They are up here. Then they go... If you just take these points, they go up here. So here, 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 here. And then suddenly, whoosh, it's flat. So clearly something seems to have happened in the flow. And we attribute this change here, we attribute to the ultimate regime. So the question is, can we find this ultimate regime also in a smaller aspect ratio experiment? Of course, anybody who is in a straight mind would say, no, you should make a larger experiment because you should get higher Rayleigh number. Why would you do lower Reynolds number? Well, the Rayleigh number, well, the reason was we had the space for it. We could put it in the same time. We could even measure at the same time one experiment and the other experiment, or exactly nominally the same conditions. And what we did is we put in thermistors again, and the sidewall thermistors. In this case, they were 50 millimeters away, and this is the sidewall thickness, which is plexiglass. So this is now the half experiment. These are the aluminum plates. And so if we do this, to our surprise, we found pretty much the same thing. So what you find is, again, so here is the Rayleigh number plotted, and in this case, there's even a much more pronounced transition, which goes up to 0.37. Well, it's not quite 0.38, but when you look at the classical state, the experiment, we find, by the way, 0.321, and the best thing we can do with the Crossman-Losey theory would be 0.323, so they agree pretty well. So this is a pretty good agreement within the error bar. And what we find, again, there's a transition to the ultimate regime, which we would call ultimate regime, where the Reynolds number clearly changes. So another time we have seen that there seems to be some signature, and surprisingly, it's a little earlier. You notice this is not 10 to the 15 anymore, this is actually below 10 to the 14. So this is kind of nice. And so what we asked ourselves as well, now we have aspect ratio 1. Well, let me talk about one effect. So here you would argue, why don't we see so much scatter here? Right? The other one scattered like mad, this one doesn't scatter. Well, the thing is, this experiment has a very well-defined mean flow. And one way to do this is you incline your experiment a little. So if you incline your experiment by, I think it was 0.1 degree or a tenth of a degree or something like that. So by inclining the experiment a little, you pin the mean flow a little more. If you want to know the exact number, Xiao will know it. And so if you explain it. But what we did is we asked ourselves, what's the impact of that? And so what we said is, what is the impact of the tilting? So since we are, here's the angle, so it's 0.7, 0.1 degree, as I said. And what you can do is, you now do the same thing again, and this is what I just showed you. And you say, well, of course, as an experimentalist, you never trust anything, and you don't trust yourself either. And so you repeat the experiment, and you do exactly the same experiment. This time you do it not inclined. And as you know, if you incline the experiment, the mean flow gets a little stronger, so the Nusselt number goes up, but the scaling did not change. So this is the same data. Well, 0 degrees, now you have to ask Xiao what the error bar is on 0 degrees, right? Because every experiment has an error bar, there's no question. But within the accuracy of the experimentalist, it's 0, and what you find is you find pretty much the same behavior, and then again, you find this transition. So what that means is even the inclination didn't matter. And so we said, well, let's go to an aspect ratio 1/3. So we built this enormous experiment. We made this thing really long. I had a conjecture that the onset of the ultimate regime should be earlier, because, or at least stay constant, because I thought it's the thermal plumes that come down from the turbulence above, and it's and the turbulence scale shouldn't change, right? So if my bottom plate is very large, and I have turbulent fluctuation with some energy injection scale, that if I have some strong vortices swiping the bottom plate, it should not change. Well, it's not true. Didn't turn out that way. What we found is that the transition happened even later. So you made this thing taller. By making it taller, the transition happened later. But this is bad news, because if I make it now even skinnier and even longer, I will not, or I make it 3 times as large, I will just never catch up to my ultimate transition. It will always evade me, right? So that's not very good. And so this was the old half data. This is the 0.3 data. And then if you plot them all 3 on the top of each other, then you find this. So you see that here is the data for 0.33, so which is here. Then you find the data 0.5, which is here. And then you find the data for 1, which is over here. Well, so this means building taller, thinner experiments, or just taller experiments, is not the way to go. What one should do is one should build wider experiment and go to larger aspect ratio. Of course, Jörg Schumacher, who loves large aspect ratios, would say, haven't I told you so? Right? Yeah, he's just smiling back there. And so we are tempted to do exactly this, and I show you this, and perhaps as a result of this conference, if not enough people convince me to build, together with Ronald and Günther and everybody in a joint effort, some kind of larger Ilmenauer Fass with SF6, with a 3-meter bottom plate. At the end of this conference, you might have convinced me to spend the rest of my career worrying about a large pot of SF6. We have just ordered, we just get another 12 tons of SF6, so we will have enough SF6 to do it. We will have 24 tons of SF6 soon, and so we can actually build a crazy experiment. But if we build one of these, I want the input from everybody to tell me what should we do, how should we do it, should we put a rotating table? I don't know, you tell me, okay? Because it will cost about 4 to 5 million to do this, and if I want to go to the Max Planck Society doing this, I need some support. My colleague, Laurent, my colleagues will say, Eberhard, yes, you better have some good reason, right, Laurent? Sure, yeah, because if I take the 5 million, they don't get it. Okay, and so what you can do is you can look at the transition range again, and so this is what the transition range was, as you see over here, and what you find is that this was the transition range, this was the actual onset of the ultimate regime, and what you realize at about an aspect ratio of, 1.5. You should already, if this extrapolation is justified, which nobody knows, right, because it might as well not be justified, you see that somewhere around 10 to the 13, these two should cross, and if they cross at above 10 to the 13, we should get Rayleigh-Bénard convection in the ultimate regime. Now, what that means is I have to build an experiment which is about 3 meters high, but which is about, 4 meters times 1.5, so this is 4.5 meters wide, 4.5 meters wide, something like that. And then I get to 10 to the 15, and then I have 2 decades of scaling. And then hopefully we have convinced everybody that this thing might actually exist that's out there. So let me summarize. So what I've shown you is that we worried, just like Ludwig, a lot about non-Boussinesq effects, especially after Ludwig's papers. We have the observation of the classical regime. We see also the ultimate regime for these different aspect ratios. It's about 0.37 plus minus 0.1. And the ultimate regime decreases with aspect ratio. Why it is 1.5, I don't know. Why this is 1.5, we don't know. It might have to do with the vortices on the side, or who knows why this is the case, why you can be so small to already see something for an infinite extended system. And we hope that if we ever build this other experiment, that we get 2 decades of scaling. Thank you very much.